the center of the Milky Way sits an object containing the mass of more than 4 million suns, and right now, almost nothing appears to be happening there. That is what worries astronomers. In galaxies across the universe, black holes of similar size are usually active. They consume gas, they heat their surroundings, they launch enormous jets of matter and radiation across intergalactic space. Ours is strangely quiet, but the deeper scientists looked, the less convincing that quiet became. In 2019, the black hole at the center of our galaxy suddenly brightened by a factor of 75 in a single night. It was the largest flare ever recorded from the object, and even today there is no agreed upon explanation. Far above and below the Milky Way, two colossal structures stretch tens of thousands of light years into space, glowing in high energy radiation. Whatever created them released energy on a scale almost impossible to comprehend. At the same time, astronomers continue to detect an unexplained surplus of gamma rays coming from the galactic center. One possible explanation would rank among the most important discoveries in modern physics. Then came another surprise. Observations revealed enormous spiral magnetic fields threading outward from the black hole itself. Similar structures in other galaxies are known to launch jets that can extend for millions of light years. The machinery appears to be there. It simply is not running, or at least not yet. The strangest detail of all may be distance. The light arriving from the galactic center tonight began its journey roughly 26,000 years ago. Whatever is happening there right now is hidden from us until the future finally catches up. What scientists are trying to understand is not just what the galactic center was, it is what it might become. Before we go any further, if you enjoy exploring the cosmos with us, a quick like or subscribe goes a long way. It helps us keep making these deep dives for curious minds like yours. Let's talk about what we actually know. Long before anyone understood what waited at the heart of our galaxy, there was only interference. A faint hiss drifted through radio equipment on Earth, arriving from a fixed direction in the sky night after night. It seemed insignificant at first, yet that distant signal marked the beginning of one of astronomy's longest investigations. We live inside the Milky Way, a barred spiral galaxy stretching roughly 100,000 light years from side to side. Within its swirling structure resides somewhere between 200 billion and 400 billion stars. From our position among them, the galaxy appears vast and crowded, yet all of that motion revolves around a common center. That center lies about 26,000 light years away, in the direction of the constellation Sagittarius. Between us and that region sits an immense veil of dust and gas. Visible light struggles to pass through it. If you looked toward the galactic core with your eyes alone, almost nothing of its true nature would reveal itself. The first clue arrived during the early 1930s. An engineer named Carl Jansky worked for Bell Telephone Laboratories, searching for sources of radio interference that affected overseas communications. To solve the problem, he built a rotating antenna measuring roughly 29 meters across, which is about 95 feet. As the instrument turned, it detected a persistent signal coming from a fixed location in the heavens. The source remained mysterious for years. As radio astronomy matured, researchers gradually realized the signal originated near the center of the Milky Way. Observatories around the world began studying that hidden region through wavelengths capable of penetrating the dust. But seeing deeper only increased the mystery. In 1974, astronomers Bruce Bialik and Robert Brown identified a compact radio source at the exact center of the galaxy. They named it Sagittarius A star. The object appeared extraordinarily bright in radio observations, yet its true nature remained uncertain. During the 1980s and 1990s, increasingly sophisticated infrared instruments transformed the investigation. Astronomers started tracking individual stars moving through the crowded environment surrounding Sagittarius A star. Some of those stars traveled at astonishing speeds. Their motions hinted at an unseen gravitational presence exerting immense influence over everything nearby. Gravity leaves fingerprints. By carefully measuring stellar orbits, researchers could calculate the mass of the hidden object responsible. In 1994, Reinhard Genzel and his collaborators showed that millions of solar masses were concentrated within a remarkably small region of space. No known cluster of ordinary stars could remain stable under such conditions. The evidence pointed toward a supermassive black hole. Years of observations strengthened that conclusion. Teams led by Reinhard Genzel and Andrea Ghez independently followed the motions of stars circling the invisible center, building one of the most compelling cases in modern astronomy. Their work continued for more than 2 decades. In 2020, both scientists shared the Nobel Prize in Physics for demonstrating what resides there. At the center of the Milky Way sits Sagittarius A star, now measured at approximately 4.297 million times the mass of our Sun. Everything we discuss from this point forward begins with that extraordinary object, hidden behind dust, shaping an entire galaxy through gravity alone. Try for a moment to shrink the entire Milky Way in your mind. Reduce its spiral arms, its star clouds, and its billions of suns until your attention settles on a single object buried at the center. Then try to imagine the weight concentrated there. Astronomers measure that weight using a unit called a solar mass. A solar mass simply means the mass of our Sun. That single star contains about 1.989 nonillion kilograms of matter. It is also roughly 333,000 times more massive than Earth. Now multiply that by approximately 4,297,000. That is the estimated mass of Sagittarius A star. The remarkable part is not merely the amount of matter involved, it is where that matter resides. All of that mass is compressed into a region smaller than the distance separating Earth from the Sun. Gravity has concentrated an extraordinary quantity of material into an astonishingly compact volume. At the edge of this region lies the event horizon. This is the boundary beyond which escape becomes impossible. Light cannot return, matter cannot return. Every future path points inward. Its scale is immense. The event horizon of Sagittarius A star has a radius of roughly 12 million kilometers, which is about 7.5 million miles. By comparison, the Sun's radius is approximately 696,000 kilometers, which is about 432,000 miles. The black hole's event horizon is therefore around 17 times wider than the Sun itself. Yet size alone does not determine behavior. Across the universe, many supermassive black holes with similar masses are surrounded by brilliant disks of infalling gas. These structures, called accretion disks, form when matter spirals inward and heats to extraordinary temperatures. Some of those black holes also launch enormous plasma jets that extend across intergalactic space, but Sagittarius A star behaves differently. Despite its tremendous mass, it consumes surprisingly little material. The surrounding environment contains gas and dust that could potentially feed the black hole, yet much of that material never reaches the event horizon. Powerful stellar winds from nearby massive stars heat and scatter the gas before gravity can fully capture it. The result is a giant that spends much of its time underfed. This remains an active area of research. Astronomers continue studying how material flows through the crowded central region and why the feeding process appears so inefficient compared with similar black holes elsewhere. Meanwhile, the stars nearest the center provide another perspective on the black hole's power. Among them is a group known as the S star cluster. These stars race through space under the direct influence of Sagittarius A star. One member, called S2, completes an entire orbit in only 16 years. During its closest approach, it reaches speeds of about 7,650 kilometers per second, which is about 4,754 miles per second. Those motions reveal more than mass. As S2 sweeps through the black hole's gravitational field, astronomers observe gravitational redshift, meaning gravity stretches the star's light to longer wavelengths. They also observe orbital precession, a gradual rotation of the orbit itself. Both effects were predicted by Albert Einstein's theory of general relativity. Here, at the center of our galaxy, those predictions unfold around a supermassive black hole with remarkable precision. For generations, the center of our galaxy existed as an absence. Astronomers could measure its influence, map its surroundings, and watch stars race around an invisible point in space. Yet the object itself remained hidden from direct view. We knew where it was. We knew what it did, but we could not see it. That began to change in 2019. After years of coordination across continents, the Event Horizon Telescope collaboration unveiled the first image ever captured of a black hole. The target was not Sagittarius A star. Instead, it was the giant black hole at the center of Messier 87, a galaxy located roughly 55 million light years away. The achievement transformed astronomy overnight. Despite its name, the Event Horizon Telescope is not a single instrument. It is a network of radio observatories spread across Earth and synchronized with extraordinary precision. Together, they function as a virtual telescope nearly the size of our planet. This technique, known as very long baseline interferometry, combines signals from distant observatories to achieve a level of detail no individual telescope could ever reach. Success with Messier 87 encouraged researchers to tackle a more familiar target, but that challenge proved surprisingly difficult. Sagittarius A star is vastly closer to us than the black hole in Messier 87. Common sense might suggest that a nearby object should be easier to photograph, yet the opposite turned out to be true. The material orbiting Sagittarius A star moves around the black hole in minutes rather than days. During observations, the structure researchers hoped to capture constantly changed shape. The target refused to stay still. Collecting enough data required sophisticated computer techniques capable of reconstructing an image from a source that seemed to rearrange itself while being observed. Years of analysis followed before the final result emerged. Then, in May of 2022, the image was revealed. At its center sat a dark shadow. Around it glowed a ring of superheated gas, moving at tremendous speed. The picture matched decades of predictions with remarkable accuracy. The shadow appeared exactly where Einstein's theory of general relativity said it should appear. The invisible object influencing the galactic center was no longer an inference drawn from measurements alone. It had a face. The image also carried an unexpected message. Researchers studying the surrounding structure noticed striking similarities between Sagittarius A star and the much larger black hole in Messier 87. Despite enormous differences in mass and behavior, both systems appeared shaped by organized magnetic fields. Those magnetic fields matter. Magnetic fields guide charged particles through space. Around active black holes, they help organize matter and channel energy outward. They are believed to play a critical role in launching enormous plasma jets that can stretch across entire galaxies. Further observations released in 2024 sharpened that picture. The data revealed strong spiral magnetic patterns threading outward from the event horizon itself. Similar structures are seen around black holes that actively launch powerful jets. The architecture is already present. The pathways exist. Deep at the center of the Milky Way, the same magnetic framework appears to be waiting, wrapped around the black hole and extending into the surrounding darkness. Sometimes discovery arrives through years of patient observation. Other times it appears in a matter of hours, forcing astronomers to question assumptions they have carried for decades. That is what happened during a spring night in 2019. Astronomer Tuan was observing Sagittarius A star using the W.M. Keck Observatory in Hawaii. The observations focused on near infrared light, a form of radiation just beyond what human eyes can detect. Similar monitoring had been conducted for years. The black hole occasionally produced brief flashes, and researchers had become familiar with its usual behavior. Then the brightness began to climb. Within only a few hours, Sagittarius A star increased in brightness by a factor of roughly 75. Nothing comparable had ever been recorded from the galactic center. The signal became so intense that Tuan later recalled wondering whether he had accidentally pointed the telescope at the wrong object. The observation was genuine. For more than 2 decades, astronomers had watched smaller flares emerge from the region surrounding the black hole. These events are thought to occur when clumps of gas fall inward or when magnetic fields suddenly release stored energy. Such flares are part of the normal rhythm of activity near Sagittarius A star. But this was different. The event immediately raised new questions about what was happening in the environment surrounding the black hole. Researchers began searching for a trigger capable of producing such a dramatic outburst. One possibility involved an object known as G2. Discovered in 2011, G2 appeared to be a compact cloud of gas and dust traveling toward Sagittarius A star. Astronomers followed it closely as it approached the black hole, expecting tidal forces to tear it apart. Tidal forces are differences in gravity across an object, strong enough to stretch and distort material moving near a black hole. Predictions were dramatic. When G2 reached its closest approach in 2014, many expected a spectacular feeding event, yet the anticipated fireworks never fully arrived. The cloud survived better than expected, leaving researchers puzzled. But some scientists proposed a delayed effect. Material stripped from G2 may have continued drifting inward over several years. By 2019, portions of that material could have reached regions close enough to trigger the extraordinary flare. Another explanation points toward a nearby star called S2. This fast moving star passed unusually close to Sagittarius A star in 2018. Its gravitational influence may have disturbed surrounding gas, setting off changes that appeared months later as a major brightening event. Neither idea has won universal acceptance. As of 2025, no single explanation fully accounts for the flare. Competing models remain under investigation, and the event continues to be studied across multiple wavelengths of light. What changed beyond dispute was our understanding of the black hole itself. Sagittarius A star had revealed a capacity for sudden and dramatic outbursts, far beyond anything previously observed. Beneath its usual appearance lies a system capable of rapid transformation, responding to conditions that astronomers are still working to understand. For one remarkable night, the center of our galaxy reminded us that it remains capable of surprises. Maps of the sky often appear complete. We imagine astronomers gradually filling in details until the picture becomes finished. Yet, every so often, an entirely new structure emerges from data that had been sitting in front of us all along. That happened in 2010. Researchers working with the Fermi Gamma Ray Space Telescope were surveying high energy radiation across the heavens when they noticed a peculiar pattern. Rising above the Milky Way and extending an equal distance below it were two enormous lobes of radiation. Their shapes were remarkably symmetrical. Their position pointed directly toward the center of our galaxy. The structures became known as the Fermi Bubbles. Their scale is difficult to grasp. Each bubble stretches roughly 25,000 light years from the galactic plane. Together, they span a distance comparable to half the diameter of the Milky Way itself. If you could somehow see them with your eyes, they would dominate the sky. The view would be astonishing. From our perspective on Earth, the bubbles would cover about 100 degrees of sky, roughly 200 times the apparent width of the full moon. Yet humanity remained unaware of their existence for so long because they glow primarily in gamma rays and X-rays, forms of radiation invisible to ordinary vision. They were hidden in plain sight. The discovery immediately created a puzzle. Structures of this size require immense energy. Calculations suggest that inflating the bubbles demanded an energy release comparable to roughly 100,000 supernova explosions occurring together. Nothing currently observed near the galactic center can account for such an event. The bubbles are evidence. They are a record preserved in radiation, documenting something that happened long ago. Astronomers soon focused on a leading explanation. Sometime between 6 million and 9 million years ago, Sagittarius A star may have experienced a dramatic feeding episode. Vast amounts of gas and dust could have fallen inward, dramatically increasing the black hole's activity. During this phase, the black hole may have briefly functioned as an active galactic nucleus, a highly energetic galactic center powered by infalling matter. The consequences would have been enormous. As material spiraled toward the black hole, powerful jets of energetic particles may have erupted above and below the galactic disk. Those jets would have pushed outward through surrounding space, inflating giant cavities that later became visible as the Fermi bubbles. But the timing adds another layer to the story. 6 million to 9 million years ago, our distant ancestors were only beginning a remarkable transition on Earth. Early members of the human lineage were learning to walk upright across African landscapes. While those first tentative steps were being taken, an event of galactic scale may have been unfolding 26,000 light years away. The bubbles remain suspended there today. They drift above and below the Milky Way like enormous fossils of energy. Their existence suggests that the center of our galaxy has not always behaved as it does now. Long before modern telescopes, long before humanity, and long before recorded history, something transformed the heart of the Milky Way and left behind structures so vast that only the most sensitive instruments could finally reveal them. Sometimes, the past announces itself through a reflection. Far from the black hole itself, immense molecular clouds drift through the inner regions of the Milky Way. These clouds contain gas, dust, and the raw ingredients from which future stars may eventually form. For years, astronomers noticed something unusual about them. Several of these clouds were glowing in powerful X-rays. The glow seemed misplaced. Nothing inside the clouds possessed enough energy to generate such radiation. No hidden star cluster explained it. No local source could account for the brightness. Yet the clouds continued shining as though illuminated by an invisible beacon. Researchers began tracing the geometry of the light. As observations accumulated, a remarkable explanation emerged. The clouds were acting like cosmic mirrors, reflecting radiation that had originated somewhere else. When astronomers reconstructed the paths involved, the reflected light pointed directly back toward Sagittarius A star. The implication was extraordinary. The black hole itself had produced a powerful burst of radiation in the past, and nearby clouds were only now revealing the event through delayed reflections. This phenomenon became known as an X-ray echo, sometimes described as a light echo. In simple terms, we are seeing ancient radiation bounce off distant structures long after the original outburst occurred. Timing studies provided another surprise. The radiation responsible appears to have been emitted roughly 100 to 400 years ago. During that period, Galileo Galilei was transforming astronomy with early telescopes. Philosophers and scientists were reshaping human understanding of nature. The first industrial machines were beginning to appear. While human history unfolded on Earth, the center of the Milky Way was experiencing episodes of activity far stronger than those observed today. But the story reaches even deeper into time. Evidence uncovered during the early 21st century suggested that Sagittarius A star experienced a much larger outburst, roughly 2 million years ago. One influential study published in 2013 estimated that the black hole may have been radiating approximately 100 million times more energy than its current output. Astronomers classify such events as Seyfert flares. A Seyfert flare occurs when a supermassive black hole enters a highly energetic feeding phase, producing intense radiation that can influence enormous regions of a galaxy. The estimated power of this ancient event would have been sufficient to ionize gas across vast distances. Ionization occurs when energetic radiation strips electrons from atoms, fundamentally altering the physical state of the gas. Evidence for this remains visible. A structure known as the Magellanic Stream stretches through space as a long ribbon of gas connecting the Milky Way with neighboring satellite galaxies. Portions of that stream display chemical signatures indicating exposure to intense radiation from the galactic center. The pattern matches what astronomers would expect if a powerful flare had erupted from Sagittarius A star in the distant past. Taken together, these clues reveal a changing system rather than a static one. Reflected X-rays, altered gas clouds, and large-scale ionization all point toward repeated episodes of activity. The center of our galaxy appears to move through cycles, spending long intervals in one state before shifting into another. We happen to observe it during a comparatively subdued chapter, while the surrounding galaxy still carries traces of everything that came before. Some discoveries arrive as a sudden breakthrough. Others linger for years, refusing to fit neatly into any explanation. Near the center of our galaxy, one such mystery has been building since the late 2000s, hidden inside vast archives of high-energy observations. The story begins with the Fermi Gamma Ray Space Telescope. As researchers mapped gamma ray emissions across the Milky Way, they noticed an unexpected surplus centered around Sagittarius A star. Gamma rays are the most energetic form of light, carrying far more energy than visible light, radio waves, or X-rays. Astronomers expected a complicated environment near the galactic center. They did not expect this. The signal was too bright. Spread across a roughly spherical region surrounding the center, the excess appeared strongest in the giga-electron-volt energy range. A giga-electron-volt is a unit used to measure particle energy, representing billions of electron volts packed into a single particle interaction. Known sources could account for much of the surrounding radiation, yet something remained. The unexplained glow persisted. Researchers eventually gave it a name, the galactic center giga-electron volt excess. More than a decade later, it remains one of astrophysics' most debated unresolved questions. The excess contributes only a small fraction of the total gamma ray emission observed within a region, extending about 30 degrees across the sky from the galactic center. But the energy involved is immense. Several explanations compete for attention. The most famous possibility involves dark matter. Dark matter is the invisible substance thought to make up most of the matter in the universe. It does not emit light and cannot be observed directly. Its presence is inferred through gravity. Some theories predict that dark matter particles can collide and annihilate each other, converting their mass into energetic radiation. Gamma rays would be produced. What captured scientific interest was how closely the observed signal matched certain predictions for dark matter annihilation. The shape of the excess and the energies involved appeared surprisingly consistent with theoretical expectations. For many researchers, this possibility transformed the puzzle into something extraordinary. But alternatives remain compelling. Another explanation proposes a hidden population of millisecond pulsars. A pulsar is a rapidly spinning neutron star, the dense remnant left behind after a massive star explodes. Millisecond pulsars rotate hundreds of times each second and can produce significant gamma ray emissions. Individually, these objects may be too faint to distinguish clearly within the crowded galactic center. Together, they could mimic the signal. Studies published through 2025 continued examining whether enough undiscovered pulsars could exist to account for the excess. Improved simulations of galactic evolution have refined those estimates, yet the debate remains active. A third possibility points back toward Sagittarius A star itself. Past outbursts may have injected energetic particles into surrounding space, creating a gamma ray halo that gradually diffused outward over time. If true, the excess would represent another lingering fingerprint of the black hole's changing history. But the stakes extend far beyond solving a regional puzzle. If dark matter annihilation ultimately proves responsible, humanity would possess its first direct observational evidence of the universe's most elusive substance. Such a discovery would reshape modern physics and alter our understanding of the cosmos itself. Long before anyone pointed a telescope toward the heart of the Milky Way, a different mystery had already begun unfolding across the universe. It emerged from motion itself. Galaxies were turning through space, and their movements refused to follow expectations. The outer stars moved too fast. According to the laws of gravity, developed by Isaac Newton and later refined by Albert Einstein, stars farther from a galaxy's center should orbit more slowly. The pattern resembles our own solar system, where distant planets travel more gradually around the Sunday. Yet when astronomers measured spiral galaxies, they found something startling. The outer regions kept pace. Stars near the edges often moved almost as quickly as those much closer to the center. The visible matter inside those galaxies could not generate enough gravity to explain what was being observed. Again and again, the calculations produced the same result. Something unseen was present. That unseen component became known as dark matter. The term does not describe a specific substance. Instead, it describes whatever is creating additional gravity while remaining invisible to every form of light we can currently detect. It does not appear to emit radiation. It does not seem to absorb it. Yet its gravitational influence shapes entire galaxies. The evidence accumulated steadily. Studies of galaxy clusters, gravitational lensing, and the large-scale structure of the universe all pointed toward the same conclusion. Today, astronomers estimate that ordinary matter, everything you can see in stars, planets, gas, clouds, and galaxies, represents only a small fraction of the universe's total content. Most of it remains hidden. The Milky Way itself appears embedded within an enormous dark matter halo extending hundreds of thousands of light years in every direction. That halo grows denser toward the galactic center, placing Sagittarius A star inside one of the most promising regions for studying this elusive component of nature. But what exactly is dark matter? For decades, one leading candidate was the weakly interacting massive particle. The name describes a hypothetical particle that would interact primarily through gravity and one of nature's fundamental forces while remaining almost completely invisible otherwise. If two such particles collided, theoretical models suggested they could annihilate each other and release gamma rays. A detectable signature might appear. What captured attention was the resemblance between those predictions and the gamma ray excess observed near the galactic center. The energy distribution and spatial pattern seemed remarkably compatible with certain dark matter models. For a time, many researchers viewed the signal as one of the strongest hints yet uncovered. Yet, the picture remains incomplete. Particle accelerators, including the Large Hadron Collider, have searched extensively for evidence of weakly interacting massive particles. Despite years of experiments, no confirmed detection has emerged. The absence of evidence has narrowed possible models, though it has not eliminated them entirely. This leaves the galactic center in a peculiar position. It may be the best place in the Milky Way to detect dark matter directly. It is also one of the most difficult regions to interpret. Pulsars, black hole activity, stellar remnants, and countless energetic processes overlap there, creating a crowded background against which any dark matter signal must be separated. So the debate continues. As observations improve and new instruments gather data, the invisible architecture surrounding our galaxy remains one of the most compelling unresolved puzzles in modern astrophysics. Imagine tracing an invisible force across the heart of our galaxy. You would expect it to follow the Milky Way's spiral shape, drifting alongside the immense lanes of stars and gas that define the galactic disk. Across most of the galaxy, that expectation holds true. Magnetic field lines generally run parallel to the spiral arms, woven into the larger structure surrounding us. But something unusual happens as we move inward. Within the central few hundred light years, the pattern changes dramatically. The magnetic fields no longer align with the galactic plane. Instead, they rise almost straight upward and downward, cutting across the disk like enormous cosmic bristles. Their orientation appears disconnected from the structure seen elsewhere throughout the Milky Way. The strength of these fields is equally remarkable. Typical interstellar magnetic fields are measured in microgauss, tiny fractions of a Gauss. Near the galactic center, astronomers detect fields reaching milligauss strengths. That may sound like a small difference, but it represents an increase of roughly 1,000 times. In cosmic terms, it is a striking departure from the norm. Radio observations reveal the most visible expression of this phenomenon. Stretching through the central region are narrow structures known as non-thermal radio filaments. These are long strands that shine primarily through radio emission rather than ordinary starlight. Some extend for 150 light years, which is about 141 trillion kilometers, which is about 88 trillion miles. Others run in nearly parallel arrangements, creating the appearance of an immense magnetic framework suspended around the galactic center. Their discovery during the 1980s immediately raised questions. Similar structures have not been observed elsewhere in the Milky Way on the same scale. Decades of study have improved our understanding, yet their exact origin remains uncertain. They appear connected to energetic particles moving through powerful magnetic channels, but the process that creates and maintains those channels continues to be debated. But recent observations have added an important clue. The Event Horizon Telescope's studies of Sagittarius A star revealed organized magnetic fields wrapped around the black hole itself. Rather than appearing chaotic, the fields formed coherent spiral patterns close to the event horizon, the boundary beyond which nothing can return. These observations suggest that the magnetic structure near the black hole may connect to the much larger architecture extending across the central galaxy. In other galaxies, similar magnetic arrangements help launch immense plasma jets. Plasma is electrically charged gas, and these jets can travel near the speed of light across extraordinary distances. The galaxy Messier 87 provides one famous example. There, magnetic fields channel matter outward in a focused beam spanning thousands of light years. Our own galaxy possesses much of the same underlying machinery. The magnetic threads are present. The organized structure exists. The central black hole is there. But the system remains largely inactive, leaving us to observe the architecture itself, waiting and enduring across cosmic time. Every massive object carries a history within its structure. Mountains preserve records of collisions between continents. Trees store seasons within their rings. At the center of our galaxy, astronomers increasingly suspect that Sagittarius A star may also carry evidence of a dramatic past, written not in rock or wood, but in gravity itself. For many years, the simplest explanation seemed reasonable. A black hole forms, gathers surrounding gas, absorbs matter from its environment, and slowly grows larger across billions of years. Under that picture, Sagittarius A star gradually accumulated mass as generation after generation of stars lived and died around it. The process was steady, incremental, predictable, but recent research has complicated that story. In September of the year 2024, researchers at the Nevada Center for Astrophysics presented evidence suggesting a different possibility. Their work combined observations from the Event Horizon Telescope with detailed models of the stellar population and gas distribution surrounding the galactic center. The results indicated that the present arrangement of matter may be easier to explain if Sagittarius A star was created through the merger of two already substantial black holes. Such an event would have been extraordinary. Imagine two enormous concentrations of gravity orbiting one another inside the young Milky Way. Over time, each pass would carry away energy through gravitational waves, which are ripples moving through space itself. Their separation would shrink. The orbit would tighten. Eventually, the two objects would collide and become one. The aftermath would be immediate. Mass that might otherwise require vast stretches of cosmic time could be assembled in a comparatively rapid event. This possibility helps explain a long-standing puzzle. Sagittarius A star contains approximately 4.297 million solar masses, yet today it appears remarkably inactive compared with many black holes of similar size. But the mystery extends beyond our own galaxy. Astronomers have discovered supermassive black holes in the early universe that already possessed enormous masses surprisingly soon after cosmic history began. According to standard growth rates, many seem to have reached their observed sizes faster than expected. This tension has encouraged scientists to explore alternative pathways capable of producing giant black holes much earlier. One proposed solution involves direct collapse. In this scenario, enormous primordial gas clouds avoid forming ordinary stars and instead collapse directly into massive black hole seeds. Later mergers then increase their size even further. A sequence of collisions occurring across billions of years could build the giants we observe today. The significance reaches far beyond Sagittarius A star itself. Observations repeatedly show that galaxies and their central black holes appear connected. Larger galactic bulges tend to host larger central black holes. Their growth seems linked through processes researchers are still trying to understand. As we examine the crowded heart of the Milky Way, we may be looking at the result of ancient encounters that shaped both structures at once. The story of Sagittarius A star is therefore more than the biography of a single black hole. It may represent one chapter in the larger story of how galaxies themselves came to be. Near the center of the Milky Way, a remarkable group of stars races through space with astonishing speed. Their paths weave around Sagittarius A star in a region so compact that, by galactic standards, it is almost unimaginably small. Here we encounter the S star cluster, one of the most puzzling stellar populations ever discovered. What makes these stars unusual is not merely where they are found, it is what they are. The cluster consists largely of massive blue stars, known as B-type stars. These objects typically possess between 10 and 30 times the mass of our Sunday. They burn their nuclear fuel rapidly and live relatively short lives. In astronomical terms, they are young, often only a few million years old. That youth creates a profound mystery. The gravitational influence of Sagittarius A star is immense. Close to a supermassive black hole, tidal forces become extremely powerful. Tidal forces are differences in gravity across an object's length, stretching and pulling material apart. Under ordinary expectations, a gas cloud approaching this region should be disrupted before it can collapse into new stars. Yet the stars exist. They are undeniably young. They are undeniably massive, and they orbit astonishingly close to the black hole itself. This contradiction has become known as the paradox of youth, a problem that continues to challenge astronomers studying the galactic center. Several explanations have been proposed. Some researchers suggest the stars formed farther from the center and gradually migrated inward through complex gravitational interactions. Others propose that an exceptionally dense disk of gas once surrounded Sagittarius A star, allowing star formation to occur despite the hostile environment. Both ideas explain part of the picture. Neither resolves every detail, but one star has become especially important. Known as S2, this object has been observed continuously for more than 25 years. It completes a full orbit around Sagittarius A star in approximately 16 years. At its closest approach, it passes within about 120 astronomical units of the black hole. An astronomical unit is the average distance between Earth and the Sunday. During that close passage, S2 reaches speeds of approximately 7,650 kilometers per second, which is about 4,754 miles per second. These observations transformed the star into a powerful laboratory for testing gravity. During its closest approach in the year 2018, astronomers measured a phenomenon called gravitational redshift. This effect occurs when powerful gravity stretches light into longer wavelengths. The measurements matched the predictions of Albert Einstein's theory of general relativity with remarkable precision. Researchers also detected Schwarzschild precession, a gradual rotation of an orbital ellipse caused by curved spacetime. The same effect helps explain the motion of Mercury around our Sun, But around Sagittarius A star, the phenomenon occurs within a gravitational field millions of times stronger. As we follow the paths of the S stars, we are not merely watching stars orbit a black hole. We are observing gravity itself reveal its structure. Each circuit around the galactic center traces another line in a map of spacetime, allowing us to measure the properties of an invisible giant with extraordinary precision. Astronomers spend much of their time predicting what the universe will do next. Every so often, the universe responds with something entirely different. In the year 2011, researchers studying the environment around Sagittarius, a star, noticed an unusual object moving toward the galactic center. It appeared as a compact source surrounded by glowing gas and dust. Named G2, the object followed an orbit that would carry it extraordinarily close to the supermassive black hole. The prediction seemed straightforward. When G2 reached periapsis, the closest point in its orbit, it would pass within roughly 130 astronomical units of Sagittarius A star. On galactic scales, that is remarkably close. Many astronomers expected the black hole's tidal forces to tear the object apart, stretching it into a long stream of material. The consequences could be dramatic. As debris spiraled inward, Sagittarius A star might experience a significant feeding event. The inflowing gas could heat up, brighten, and produce an observable outburst from the center of the Milky Way. Observatories around the world prepared to watch the encounter unfold. Years of anticipation followed. By the time the year 2014 arrived, telescopes across multiple wavelengths were tracking the event closely. Researchers expected to witness one of the most spectacular interactions ever observed near the galactic center. Then G2 arrived, and almost nothing happened. The object became distorted during its passage. Gravity clearly affected it, yet the catastrophic destruction predicted by many models never occurred. G2 survived the encounter far better than expected and continued on its orbit. That outcome forced astronomers to rethink the object's nature. A pure gas cloud should have been much more vulnerable to tidal disruption. Evidence increasingly suggested that G2 contained something denser at its center. The leading explanation today proposes that it may be the product of two stars that merged together, creating a stellar object wrapped in a shell of gas and dust. Such a core could survive. While surrounding material might be stripped away, the central object would remain intact. This interpretation fits the observations more successfully than the original picture of an isolated gas cloud drifting toward destruction. But the encounter may still have left a mark. Some material appears to have been removed from G2 during its passage. Over the following years, that gas continued moving through the crowded environment around Sagittarius A star. Several researchers have suggested that part of this stripped material may eventually have drifted inward. That possibility remains intriguing. The extraordinary flare observed in the year 2019 occurred roughly 5 years later. Although no direct connection has been confirmed, some studies suggest delayed infall from G2 could have contributed to the event. More importantly, G2 revealed how unpredictable the galactic center can be. Even when observations seem clear and theories appear sound, Sagittarius A star continues to challenge expectations, reminding us that the heart of our galaxy still holds surprises. At first glance, the center of our galaxy seems like a place where a supermassive black hole should be feasting constantly. Massive stars crowd the region, gas drifts through the surrounding environment, energy flows in every direction. Yet Sagittarius A star remains surprisingly restrained. That contradiction has fascinated astronomers for decades. Compared with black holes of similar mass in other galaxies, Sagittarius A star emits remarkably little radiation. Many supermassive black holes are surrounded by brilliant accretion disks, glowing structures of infalling material heated to extreme temperatures. Some launch enormous jets that stretch across intergalactic space. Our galactic center behaves differently. Part of the explanation comes from a process known as radiative inefficiency. In simple terms, the gas moving inward becomes extremely hot and diffuse before reaching the black hole. Instead of converting much of its energy into visible radiation, the gas carries a large fraction of that energy away with it. The result is surprisingly dim, yet fuel is available. Throughout the central region, young massive stars continuously release material through powerful stellar winds. These winds are streams of gas flowing outward from stellar surfaces at tremendous speeds. Collectively, they inject significant amounts of matter into the environment surrounding Sagittarius A star. You might expect that material to fall inward, but the journey is more complicated. A study published in the year 2020, using observations from the Chandra X-ray Observatory, revealed that only a tiny fraction of this available gas ultimately reaches the event horizon. The event horizon is the boundary beyond which nothing can escape the black hole's gravity. The numbers are striking. Roughly 1% of the material supplied by nearby stellar winds appears to make it all the way inward. The remaining 99% is prevented from completing the journey. Collisions between different wind streams generate intense heating. As temperatures rise, much of the gas gains enough energy to flow outward again rather than continue falling inward. The system regulates itself. The same stars that provide potential fuel also help prevent accretion. Their collective activity creates a turbulent environment that limits how efficiently the black hole can feed. In a sense, the neighborhood continually disrupts its own supply chain. But this balance may not be permanent. Astronomers have found evidence that larger reservoirs of colder and denser gas occasionally move toward the galactic center. Some of this material appears to travel along the Milky Way's central bar, an elongated structure crossing the inner galaxy. These inflows are difficult to predict. When cold gas arrives, it behaves differently from the hot diffuse material produced by stellar winds. Dense clouds can resist heating more effectively and may penetrate deeper into the central environment. If enough material arrives at once, the existing regulation mechanism could become overwhelmed. For now, Sagittarius A star remains underfed, yet the conditions surrounding it suggest that the situation is never entirely stable. The heart of the Milky Way appears less like a dormant system and more like a delicately balanced one, constantly adjusting the flow of matter around a black hole that is always waiting for its next opportunity to feed. Imagine standing at the edge of a region where stars crowd together so densely that familiar ideas of space begin to lose meaning. Around Sagittarius, A star lies such a place, a compact realm known as the nuclear star cluster. This is the most crowded, stellar environment in the Milky Way. Near our Sun, stars are separated by vast distances. Interstellar space feels open and expansive. At the galactic center, conditions are dramatically different. The stellar density reaches roughly 10 million stars per cubic parsec. By comparison, the neighborhood surrounding our own Sun contains only about 0.14 stars per cubic parsec. The contrast is astonishing. The central region is approximately 70 million times more crowded than the part of the galaxy we call home. Within only a few light years, stars of many different ages occupy overlapping orbits around the galactic center. Their histories are complex. Observations reveal multiple stellar populations formed during different eras. Some stars are relatively young, others have existed for billions of years. Together, they suggest repeated episodes of star formation unfolding throughout the history of the Milky Way. But visible stars tell only part of the story. Hidden among them are the remnants of countless earlier generations. White dwarfs, the compact cores left behind by sun like stars, populate the region. Neutron stars, crushed remnants of massive stellar explosions, are expected to be abundant as well. Stellar mass black holes likely move through the cluster in significant numbers. Many may be concentrated near the center. A study published in the year 2018 examined X ray binary systems and found evidence suggesting thousands of stellar mass black holes could occupy the inner few light years around Sagittarius A star. Over immense spans of time, these heavy objects gradually migrate inward through a process called dynamical friction. The mechanism is surprisingly simple. As massive objects travel through a sea of lighter stars, countless gravitational interactions slowly rob them of momentum. The heavier bodies drift inward, while lighter stars gain energy and move outward. Over millions of years, the central region becomes increasingly populated by compact remnants. This creates extraordinary possibilities. Some of these smaller black holes may eventually enter long spirals toward Sagittarius A star itself. Astronomers call such events extreme mass ratio in spirals. In these systems, a relatively small black hole slowly circles a vastly larger one while losing energy through gravitational waves. The process can continue for ages. Future observatories may detect these signals directly. The planned Laser Interferometer Space Antenna mission is expected to search for precisely this type of gravitational wave source during the coming decades. Beyond the stars and remnants lies another important structure, a massive ring of gas and dust, known as the circumnuclear disk, circles the galactic center between roughly 1.5 and 7 light years from Sagittarius A star. It serves as a long-term reservoir of material, a reminder that even in this crowded environment, the ingredients for future activity continue to orbit at the heart of the Milky Way. A fresh layer of the galactic center's history emerged from radio waves rather than visible light. In the year 2019, while astronomers continued examining unusual activity near Sagittarius A star, another discovery reshaped the larger picture. The finding came from the Meerkat radio telescope in South Africa. Spread across the Karoo Desert, the array's 64 dishes were designed to detect faint structures that previous instruments often blended into the background. When researchers mapped the central regions of the Milky Way in unprecedented detail, they uncovered something remarkable. Two enormous radio-emitting lobes appeared above and below the galactic plane. Each structure stretched roughly 1,400 light-years from the center. Together, they formed a symmetrical pair, aligned around Sagittarius A star and extending perpendicular to the galaxy's disk. Their shape immediately invited comparison with the much larger Fermi bubbles already known from gamma-ray observations. Yet these were different. The newly discovered structures occupied a smaller volume and appeared nested within the larger bubbles. Their boundaries looked sharper. Their radio signatures followed different patterns. Their physical characteristics suggested they were not simply another view of the same phenomenon, but the similarities remained difficult to ignore. Estimated ages for the radio bubbles fall within a range of roughly 6 million to 9 million years. That timing overlaps strikingly with leading age estimates for the Fermi Bubbles. Such agreement hints at related activity in the galactic center's past, though the exact connection remains uncertain. Several possibilities remain under consideration. One interpretation proposes that the radio bubbles formed during a separate energetic episode occurring after the larger event that inflated the Fermi bubbles. If correct, the galactic center may have experienced multiple bursts of activity rather than a single dramatic outflow. The evidence points toward repetition. Instead of one isolated eruption, Sagittarius A star may have cycled through episodes of enhanced feeding and energy release. Each event would leave behind a distinct signature. Over millions of years, those signatures accumulate, creating a layered record embedded within the structure of the galaxy itself. Radio observations are particularly valuable here. Unlike visible light, radio waves can penetrate regions crowded with dust and gas. They reveal structures otherwise concealed from view. Meerkat's exceptional sensitivity allowed astronomers to separate these faint emissions from surrounding radio noise and trace their full extent with unusual clarity. But the radio bubbles are only one piece of a growing puzzle. Around the galactic center, we now find vertical magnetic filaments, reflected X-ray echoes, mysterious gamma-ray excess emissions, radio bubbles, and the enormous Fermi bubbles beyond them. Each structure occupies a different scale. Each preserves information from a different period. Together they resemble a layered geological record written across space. When you step back and view all these features at once, the galactic center begins to look less like a stable environment and more like a place with a long memory. The structures surrounding Sagittarius A star appear to preserve traces of repeated awakenings, each one leaving behind evidence that survives long after the original event has faded from view. Sometimes a discovery does not replace an older picture. It expands it until the earlier version seems incomplete. That is what happened when a new generation of X-ray observations turned toward the heart of our galaxy. In the year 2020, the extended Roentgen survey with an imaging telescope array telescope began surveying the sky in X-rays. The mission was designed to map energetic structures across the universe with unprecedented sensitivity. Almost immediately, it revealed something astonishing surrounding the Milky Way. Two immense X-ray emitting lobes stretched above and below the galactic plane. Their scale was extraordinary. The structures extended roughly 45,000 light-years in each direction from the center, far beyond the already enormous Fermi bubbles. Together, they formed the largest coherent structures ever associated with our galaxy. What had once seemed immense now appeared to be only part of a much larger system. The geometry was difficult to ignore. The newly discovered X-ray structures appeared to envelop the Fermi bubbles, surrounding them like a larger shell. Their alignment pointed directly back to the same central region. Their symmetry suggested a common origin. Rather than representing an unrelated phenomenon, they appeared connected to the same ancient history recorded by the gamma-ray structures nested inside them. But the implications reached further. If the X-ray bubbles mark the outer shock front of an ancient outburst, then we are seeing the boundary where energy from the galactic center plowed into surrounding material. A shock front is the compressed edge produced when a powerful disturbance travels through gas. As that disturbance expands, it sweeps up matter and leaves a glowing signature behind. The X-ray emission fits that picture remarkably well. Researchers proposed that a major eruption from Sagittarius A star launched an enormous blast wave millions of years ago. As the wave expanded outward, It compressed the thin material surrounding the galaxy. The resulting shock heated that material and caused it to radiate in X rays, creating the vast structures now visible across the sky. Energy estimates increased accordingly. The Fermi bubbles alone already implied a tremendous release of power. Once the larger X ray structures were incorporated into the calculations, the total energy required became even greater. The ancient event responsible for shaping these features may have been substantially more violent than earlier models suggested. A pattern has gradually emerged from decades of observations. Each new instrument arrives with sharper vision. Each survey reaches deeper sensitivity. Each generation uncovers structures that previous telescopes could not detect. What once appeared isolated becomes connected. What seemed large becomes part of something larger still. But the overall trend remains remarkably consistent. As our ability to observe improves, the galactic center does not become simpler. Additional layers continue appearing. More relics emerge from the data. The history recorded around Sagittarius A star grows richer and more complex, revealing a central engine whose influence extends across distances measured not in planets or stars, but in tens of thousands of light years. A distant spiral galaxy became unexpectedly important to our story in the year 2025. The reason was not its beauty. Many spiral galaxies are beautiful. The reason was what astronomers discovered hidden within its center. An international research team, led by Christ University in Bangalore, examined a galaxy known as 2 Micron All Sky Survey Extended Source, J2345328-0449256. Located roughly 1 billion light years from Earth, the galaxy spans a region about 3 times larger than the Milky Way. At first glance, it appeared familiar. Its spiral arms remained clearly defined. A luminous central bar crossed its inner regions. Stars traced orderly patterns through its disk. From a distance, you might see nothing unusual at all. But deeper observations revealed another reality. Using the Hubble Space Telescope, the Giant Microwave Radio Telescope, and the Atacama Large Millimeter Array, astronomers found evidence of an extremely active supermassive black hole at the galaxy's center. That black hole was producing colossal radio jets. Streams of magnetized plasma launched outward from the galactic nucleus at tremendous speeds. The scale was astonishing. Those jets extended roughly 6 million light years through space, making them among the largest known jet structures associated with any spiral galaxy. Their reach exceeded the diameter of the Milky Way many times over. Yet despite such extraordinary activity, the host galaxy remained structurally intact. That result challenged long-standing assumptions. For many years, astronomers expected jets of such power to severely disrupt spiral galaxies. Energetic outflows can heat gas, alter star formation, and reshape galactic environments. The expectation was that sustained activity on this scale would leave obvious scars throughout the host galaxy. But the observations suggested something different. The spiral arms persisted. The stellar ring remained recognizable. The overall architecture survived. Powerful activity in the nucleus and large-scale order across the galaxy appeared capable of existing together for extended periods. For researchers studying Sagittarius A star, the implications were impossible to ignore. Theoretical models have long suggested that our galaxy's central black hole possesses the physical ingredients required for more active phases. We have already encountered evidence of ancient eruptions recorded in enormous structures surrounding the galactic center. This distant galaxy offered a living example of what such activity might resemble when viewed on a grand scale. Not a destroyed galaxy, a transformed one. If Sagittarius A star were to enter a substantially more energetic state, the inner regions of the Milky Way could experience dramatic changes while the familiar spiral pattern endured. The galaxy might continue looking recognizable from afar, even as powerful processes unfolded deep within its core. That possibility reframes how we think about calm appearances. When you observe the Milky Way today, it is tempting to assume stability implies inactivity. Yet, this distant spiral galaxy demonstrates that a peaceful exterior can coexist with extraordinary events at its center. The observation serves as a reminder that galaxies are not fixed structures. They evolve through cycles of activity, and sometimes the most dramatic chapters remain hidden behind an outwardly familiar face. A single dramatic outburst naturally attracts attention, yet the everyday behavior of Sagittarius A star may be just as revealing. Beneath the rare events that dominate headlines lies a persistent rhythm of smaller eruptions occurring far more often than many people realize. The galactic center is active every day. Long-term monitoring campaigns have shown that Sagittarius A star regularly produces detectable flares in both X-ray and infrared light. Observations from the Chandra X-ray Observatory and the gravity instrument attached to the Very Large Telescope Interferometer indicate that these brightenings occur roughly once or twice each day. Most are modest. A typical flare lasts from several tens of minutes to a few hours before fading again. The underlying causes appear to involve processes unfolding extremely close to the event horizon, where gravity, magnetism, and high-energy particles interact under conditions impossible to reproduce on Earth. One important mechanism is magnetic reconnection. Magnetic reconnection occurs when magnetic field lines suddenly rearrange themselves and release stored energy. Similar processes occur on the Sun, though the environment around a supermassive black hole is vastly more extreme. Near Sagittarius A star, these magnetic disruptions can accelerate particles and generate brief bursts of radiation detectable across enormous distances. But magnetic activity is only part of the story. Small amounts of surrounding material occasionally drift inward and enter the accretion zone, the region where matter begins spiraling toward the black hole. Even modest infall can trigger noticeable increases in brightness, producing another category of flare observed by astronomers. Some of the most fascinating observations involve structures known as hotspots. These are compact concentrations of extremely energetic plasma orbiting near the black hole during flare events. Infrared measurements have allowed researchers to track their motion directly. In several cases, these bright regions completed an orbit in approximately 45 minutes. The speed is extraordinary. Models indicate orbital velocities approaching roughly 36% of the speed of light. At such speeds, the effects predicted by Albert Einstein's theory of general relativity become impossible to ignore. Light is distorted, time behaves differently, space itself is warped by gravity. For scientists, these hotspots are valuable laboratories. Their trajectories provide direct tests of physics in one of the strongest gravitational environments accessible to current instruments. Every orbit supplies new information about how matter behaves near a supermassive black hole. But these daily flares also raise a deeper statistical question. If small brightenings occur every day, and exceptionally large events appear only after years or decades, how are those events connected? Does the same underlying process produce both? Are rare giant outbursts simply the extreme end of a continuous distribution, or do they arise through entirely different mechanisms? At present, the evidence remains incomplete. Detailed monitoring spans only about 25 years. Against a history measured in millions of years, that record is remarkably brief. We are attempting to understand long term behavior from a very narrow observational window. For now, you and I are watching only a short fragment of a much longer cycle, one still unfolding around the dark heart of our galaxy. Long before any telescope captures an image, space itself can carry a message. When massive objects move through intense gravitational fields, they disturb the structure of spacetime around them. Those disturbances travel outward as gravitational waves, faint ripples spreading across the universe at the speed of light. Unlike ordinary light, they pass through gas, dust, and entire galaxies almost unchanged. They preserve the story. The first direct detection arrived on September 14th, 2015. Scientists working with the Laser Interferometer Gravitational Wave Observatory recorded a signal from two merging stellar mass black holes located about 1.3 billion light-years away. The event lasted less than a second, yet it changed astronomy forever. For the first time, humanity detected a cosmic event through the motion of spacetime itself. The signal confirmed a major prediction of Albert Einstein's general theory of relativity and opened an entirely new way of observing the universe. But the black hole at our galactic center speaks in a different register. The Laser Interferometer Gravitational Wave Observatory is designed to detect relatively high-frequency gravitational waves, typically produced by mergers involving stellar mass black holes and neutron stars. These signals oscillate roughly between 10 and 1,000 cycles per second. Sagittarius A star operates on slower timescales. Near the galactic center, smaller black holes are expected to gradually spiral inward toward the supermassive black hole over immense periods. These events generate much lower frequency waves, measured in thousandths of a cycle per second. Existing ground-based detectors cannot sense them. A different instrument is required. The European Space Agency's Laser Interferometer Space Antenna mission is being developed specifically for this challenge. Instead of remaining on Earth, it will operate in space using 3 spacecraft flying in a giant triangular formation around the Sunday. The scale is astonishing. Each side of the triangle will measure approximately 2.5 million kilometers, which is about 1,553,000 miles. Laser beams will travel continuously between the spacecraft, monitoring tiny changes in distance caused by passing gravitational waves. The measurements must be extraordinarily precise. Scientists expect the system to detect shifts smaller than a fraction of an atomic diameter. Such sensitivity would allow the observatory to register signals produced by objects moving around supermassive black holes throughout the universe. Launch is currently planned for the 2030s. Among its most important targets are extreme mass ratio and spirals, events in which a smaller black hole slowly spirals toward Sagittarius A star over millions of years. Every orbit carries information. Every gradual descent writes details into the gravitational wave signal. Those details matter. The waves encode the mass, rotation, and geometry of the objects involved. By studying their patterns, astronomers can map the structure of spacetime surrounding the black hole with remarkable accuracy. For decades, We have estimated the properties of Sagittarius A star through light, motion, and indirect evidence. But a new era is approaching. Soon, you and I may study the galactic center through vibrations traveling across the universe itself, reading the shape of gravity as it moves through space. Across distant deserts, construction is underway on an instrument unlike any radio observatory that came before it. Spread between South Africa and Australia, the Square Kilometer Array is being designed to examine the universe with extraordinary sensitivity. Thousands of individual antennas will work together across vast distances, functioning as a single coordinated observatory. When complete, its effective collecting area will approach 1 square kilometer, which is about 0.39 square miles. The scale is immense, yet one of its most important destinations lies within our own galaxy. Among the observatory's major scientific goals is a deeper exploration of the region surrounding Sagittarius A star, where many of the questions we have followed remain unresolved. In 2024, later updated in 2025, an international group of 20 researchers proposed a dedicated galactic center survey using the Future Observatory. Their plan focused on a region roughly 180 parsecs long and 40 parsecs wide, centered on Sagittarius A star. That corresponds to approximately 587 light years by 130 light years. The proposal reaches beyond a simple snapshot. Researchers also recommended repeated observations, extending across an entire decade. By revisiting the same region again and again, astronomers hope to watch subtle changes unfold in real time, revealing processes that current instruments cannot track clearly. Several mysteries stand waiting. One involves pulsars, rapidly rotating neutron stars that emit beams of radio energy. These objects act like remarkably precise clocks. If enough pulsars are discovered within the nuclear star cluster, scientists may finally determine whether they are responsible for the unexplained gamma ray excess observed near the galactic center. But pulsars offer something even more valuable. Every pulse traveling through the warped spacetime surrounding Sagittarius A star carries information about gravity itself. Tiny distortions in the arrival times of those signals can reveal how space and time behave in one of the strongest gravitational environments accessible to observation. This technique is known as pulsar timing. In simple terms, astronomers compare the expected rhythm of a pulsar with the rhythm actually received on Earth. Differences between the two can expose subtle effects predicted by general relativity, often with astonishing precision. The observatory is expected to map other structures as well. Long magnetic filaments stretching through the galactic center may finally reveal their full three-dimensional geometry. Flows of gas moving toward the black hole could be traced with far greater detail. Short-lived transient events, sudden outbursts that appear and vanish quickly, may also emerge from the background for the first time. Each improvement sharpens the picture. Current observations often resemble glimpses through scattered openings. The Square Kilometer Array promises something closer to a continuous view, connecting isolated discoveries into a larger framework. Perhaps the most exciting possibility involves finding a pulsar in a tight orbit around Sagittarius A star itself. Such an object would circle through extreme gravity while broadcasting an extraordinarily stable signal. Many physicists regard that scenario as the ultimate natural laboratory for testing gravity in the observable universe. For now, the search continues. But the next great eye aimed toward the galactic center is already taking shape beneath southern skies. After following clues scattered across radiation, magnetic fields, stellar motions, and ancient outbursts, we arrive at the question that sits beneath them all. What would happen if Sagittarius A star entered another major active phase? The answer is less apocalyptic than many imagine. If the black hole began consuming large amounts of matter, it would likely transform into what astronomers call a low luminosity active galactic nucleus. In simple terms, that means the region around the black hole would become extraordinarily bright as infalling gas released vast amounts of energy before crossing the event horizon. The change would be dramatic. During peak activity, Sagittarius A star could become roughly 10 billion times brighter than it is today. For a time spanning thousands or even millions of years, the galactic center would radiate across the electromagnetic spectrum with an intensity far beyond its current state. From Earth, the view would change. Our planet lies about 26,000 light years from the galactic center. Even at that distance, the nucleus of the Milky Way would become noticeably brighter. Dense clouds of intervening dust would continue blocking much of the visible light, yet the central region would no longer appear as dormant as it does today. But visible brightness is not the primary concern. The more significant consequence involves high energy radiation. Active galactic nuclei produce powerful emissions of X rays and gamma rays. Evidence preserved in molecular clouds and distant gas structures indicates that Sagittarius A star generated similar radiation during past episodes of heightened activity. Fortunately, distance matters enormously. As radiation spreads outward, its intensity decreases according to the inverse square law. This principle states that energy becomes diluted across a rapidly expanding area. By the time radiation from a major outburst traveled 26,000 light years to Earth, it would be far weaker than many popular portrayals suggest. Direct biological danger remains unlikely. A more intriguing possibility involves the formation of relativistic jets, narrow streams of magnetized plasma accelerated to velocities approaching the speed of light. Observations of other spiral galaxies demonstrate that central black holes can produce such structures while the galaxies themselves retain their recognizable spiral forms. But geometry becomes important. Jets emerging from a supermassive black hole generally extend perpendicular to the galactic disk. Earth resides within that disk, orbiting far from the center. If Sagittarius A star launched large jets, they would most likely fire above and below the plane of the Milky Way rather than through it. The largest consequences would unfold elsewhere. Over millions of years, energy deposited into the galactic halo could heat enormous reservoirs of gas surrounding the galaxy. Those reservoirs provide raw material for future generations of stars. Altering their temperature changes how efficiently new stars can form. Astronomers call this process active galactic nucleus feedback. It is considered one of the fundamental mechanisms governing galactic evolution throughout the universe. In that sense, a reawakened Sagittarius A star would not threaten Earth directly. Instead, it would slowly reshape the long-term future of the Milky Way itself, influencing how the galaxy grows, ages, and creates stars across cosmic time. Step back far enough from any galaxy, and a remarkable pattern begins to emerge. The stars, gas, clouds, and spiral arms may appear to dominate the scene, yet observations gathered across decades reveal a deeper relationship. At the heart of nearly every large galaxy sits a supermassive black hole, and its influence extends far beyond the region immediately surrounding it. The connection is profound. One of the most significant discoveries in modern cosmology is that galaxies and their central black holes do not evolve independently. Instead, They appear to regulate one another through a process known as active galactic nucleus feedback. The idea is surprisingly simple. When a supermassive black hole enters an active phase, matter falling inward releases enormous amounts of energy. That energy spreads outward through radiation, winds, and sometimes powerful jets. Gas that might otherwise cool and collapse into new stars becomes heated, disrupted, or expelled from the galaxy's inner regions. Star formation slows. In some cases, it nearly stops altogether. Evidence for this relationship appears across surveys containing thousands of galaxies observed at different stages of cosmic history. Astronomers repeatedly find a striking correlation between the mass of a galaxy's central black hole and the mass of its stellar bulge, the densely populated central region surrounding the nucleus. This relationship is known as the mass sigma relation. Sigma refers to the average motion of stars within the bulge. The tighter the relationship became through observation, the harder it was to dismiss as coincidence. Somehow, black hole growth and galaxy growth remain linked across billions of years. But the mechanism is not subtle. When a supermassive black hole becomes highly active, the energy it releases can transform an entire galaxy. Gas reservoirs that would have produced future generations of stars become heated beyond the point where collapse occurs efficiently. Over time, stellar birth rates decline. The largest elliptical galaxies provide compelling examples. Many contain vast populations of ancient stars, but very little ongoing star formation. Astronomers believe their central black holes played a major role in creating that condition, regulating the available gas until the galaxies entered long periods of relative inactivity. Our own galaxy appears to have participated in the same cycle. The giant gamma ray structures, known as the Fermi Bubbles, the enormous X-ray features discovered by the extended Röntgen survey with an imaging telescope array observatory, the reflected X-ray echoes preserved within molecular clouds, and the ionized gas associated with the Magellanic Stream all point toward episodes when the galactic center released far more energy than it does today. These clues form a consistent picture. The present state of Sagittarius A star is not necessarily permanent. It represents one stage within a much longer cycle of activity and decline. Throughout that cycle, the central black hole influences how gas moves, how stars form, and how chemical elements become distributed throughout the galaxy. In a very real sense, the history of the Milky Way is partly the history of its black hole. The conditions that eventually allowed planetary systems like ours to emerge were shaped by processes unfolding at the galactic center across immense stretches of cosmic time. Across the observable universe, galaxies appear in astonishing variety. Some are delicate spirals filled with young stars. Others are giant elliptical systems shaped by ancient mergers. Yet beneath those differences lies a recurring feature. At the center of nearly every large galaxy resides a supermassive black hole, and the lessons gathered from our own galactic center help us understand them all. This is where proximity matters. Sagittarius A star is not the largest known black hole. It is not the brightest. It is not even particularly active. Yet it sits close enough for us to examine details that remain inaccessible almost everywhere else. That advantage changes everything. A useful comparison comes from the black hole at the center of the galaxy Messier 87. This object, known as Messier 87 star, became famous in 2019 when the Event Horizon Telescope produced humanity's first direct image of a black hole shadow. Its scale is immense. Messier 87 star contains roughly 6.5 billion times the mass of our Sun, more than 1,500 times the mass of Sagittarius A star. Unlike our comparatively subdued galactic center, it currently powers a relativistic jet, a stream of matter moving near the speed of light, extending roughly 5,000 light years into surrounding space. The contrast appears dramatic. One black hole feeds actively, the other remains comparatively restrained. One launches a visible jet, the other shows no comparable structure today. Yet, when astronomers compared observations from the Event Horizon Telescope, surprising similarities emerged. The magnetic field patterns looked remarkably alike. Despite enormous differences in mass, environment, and activity level, both systems displayed organized magnetic structures surrounding their event horizons. Those observations suggested that the fundamental physics governing accretion, the process of matter falling inward, may operate according to universal rules. The same principles appear repeatedly. Gravity shapes the flow of matter. Magnetic fields guide energy. Rotating gas forms disks. Under suitable conditions, jets emerge. The details vary from galaxy to galaxy, but the underlying mechanisms remain strikingly consistent. This realization elevates the importance of every observation made near Sagittarius A star. When we measure a stellar orbit, we refine models used throughout the cosmos. When a flare erupts, we gain insight into processes occurring around distant galactic nuclei. When magnetic structures are mapped near the event horizon, those measurements become reference points for interpreting observations far beyond the Milky Way. Distance limits other systems. If Messier 87 existed where Sagittarius A star does, we could resolve countless surrounding details. We would watch individual stars move. We would track gas clouds directly. We would study its environment with extraordinary precision. But at its actual distance, many of those structures remain beyond current observational reach. Our galactic center, therefore, serves a special role. It functions as a nearby laboratory where theories can be tested against direct evidence. Each confirmed prediction strengthens our ability to interpret galaxies scattered across billions of light years. In that sense, Sagittarius A star becomes more than the black hole at the center of our galaxy. It is a key for translation. By learning to read this one system in extraordinary detail, we gain the ability to understand countless others spread throughout the observable universe. A map can become extraordinarily detailed while still containing blank spaces. That is where we find ourselves today. After decades of observations spanning radio waves, infrared light, visible light, X-rays, gamma rays, and now the emerging era of gravitational wave astronomy, the galactic center remains filled with mysteries that resist simple answers. Each discovery sharpens the picture, yet each improvement reveals new uncertainty. Some questions remain especially persistent. One of the most debated involves the galactic center giga-electron-volt excess, a surplus of gamma-ray radiation detected around the heart of the Milky Way. Researchers have proposed several explanations. One possibility is a hidden population of pulsars, rapidly rotating neutron stars, emitting beams of radiation. Another possibility involves dark matter, the invisible substance thought to account for most matter in the universe. But neither explanation has achieved broad consensus. The evidence remains incomplete. Another puzzle emerged dramatically during the remarkable brightening event of 2019, Sagittarius. A star increased in brightness by roughly 75 times within a single night. Astronomers observed it. They measured it. Yet no definitive explanation has been established. Was the flare triggered by infalling material, magnetic activity, or some process still unrecognized? The answer remains uncertain. Patterns are difficult to identify. The enormous structures extending above and below the galaxy raise another unresolved question. What exactly created the Fermi bubbles? Did a single feeding episode unleash the energy responsible? Was it sustained jet activity lasting thousands of years? Could intense star formation have contributed through powerful stellar winds? Several possibilities fit portions of the evidence. Closer to the black hole, the mystery deepens further. Massive young stars continue orbiting where conventional models suggest they should never have formed. Their presence challenges established theories of star formation. New observations have improved constraints, but no explanation fully accounts for every characteristic of these unusual stellar populations. The problem endures. Magnetic fields introduce another layer of uncertainty. We know they influence gas motion, flare production, and energy transport near Sagittarius A star. But what is their true three-dimensional structure? How do field lines connect the event horizon to the surrounding environment? Existing observations provide fragments of the answer rather than a complete picture. Much remains hidden. Even the long-term behavior of Sagittarius A star is difficult to interpret. Are recent observations capturing a gradual increase in activity? Are they revealing a decline from an earlier state? Or are we simply witnessing ordinary fluctuations around a stable average? A few decades of measurements represent only a brief moment compared with the timescales governing galactic evolution. Perspective matters. Researchers also continue searching for the population of stellar mass black holes expected to crowd the inner region of the galaxy. How many are truly present? How often do they spiral inward and merge with the central black hole? Future gravitational wave observatories may finally provide direct answers. But every solution is likely to create new mysteries. The square kilometer array, the laser interferometer space antenna, the extremely large telescope, and future generations of the Event Horizon Telescope were designed with questions like these in mind. Their observations may resolve some of today's uncertainties, yet science rarely closes the book. More often, it turns the page, revealing a deeper layer beneath the one we thought we understood. Numbers sometimes lose their meaning when they grow too large. We can recite them easily. We can write them down. Yet the mind struggles to transform them into something tangible. The distance separating Earth from Sagittarius A star belongs to that category. The galactic center lies approximately 26,000 light-years away, a span so immense that ordinary intuition begins to fail. The scale is difficult to hold. A single light-year represents the distance light travels in 1 year, roughly 9,460,000,000,000 kilometers, which is about 5,880,000,000,000 miles. Multiply that by 26,000, and the result becomes almost impossible to picture in any meaningful human sense. The numbers stretch beyond experience. That distance carries another consequence. Every photon arriving from Sagittarius A star began its journey 26,000 years ago. The information reaching our telescopes tonight departed the galactic center long before recorded history. It started traveling across space when Upper Paleolithic communities still occupied Europe, creating paintings and caves that survive to this day. The message is ancient. No city existed then, no written language, no agriculture, no kingdoms. Entire civilizations that would later rise and disappear remained unimaginably far in the future when that light first left the center of the Milky Way. We are always looking backward. What is happening near Sagittarius? A star at this exact moment remains hidden from us. Whatever events unfold there today will not become visible on Earth until 26,000 years from now. Future observers, living in a world we cannot imagine, will receive the light that is being emitted there at this very instant. The galactic center arrives late. In that sense, astronomy becomes a form of archaeology. Telescopes do not reveal the present. They reveal preserved history carried by light across vast stretches of space. Each observation reconstructs a chapter already completed long ago. But distance provides more than perspective. It also provides protection. Energy spreads outward as it travels. This behavior is described by the inverse square law, a principle stating that radiation becomes weaker as it expands across an ever-growing sphere. The farther energy travels, the more widely it disperses. Intensity falls rapidly. Even if Sagittarius A star experienced a major energetic outburst, that radiation would have to cross 26,000 light-years before reaching Earth. By the time it arrived, the energy would be diluted across an enormous volume of space. Additional shielding would come from Earth's atmosphere, Earth's magnetic field, and the protective influence of the Sun's magnetic environment. Several safeguards exist. This perspective reshapes the way we think about the galactic center. The most energetic region in our galaxy is real. Its history includes eruptions, radiation, and episodes of astonishing power. Yet those events unfold at a distance so extraordinary that their effects reach us primarily as faint traces collected by sensitive instruments. The universe can be violent, but it is also vast. That vastness separates us from many of its greatest upheavals. 26,000 light-years transforms catastrophe into data, turning the drama of the galactic center into delicate signals that drift across deep time before finally arriving at our small corner of the Milky Way. Before any discovery could be made, a different challenge had to be solved. The center of our galaxy hides behind vast clouds of dust and gas. Visible light struggles to cross that barrier. For centuries, human observers could see the bright band of the Milky Way stretching overhead, yet the true nature of its core remained concealed. The destination was there all along. We simply lacked the tools required to reach it. Progress arrived gradually. In the early 1930s, an engineer named Carl Jansky was investigating sources of interference affecting transatlantic radio communications. His rotating antenna detected a persistent signal that repeated every sidereal day, a day measured by the stars rather than the Sunday. Careful analysis revealed an unexpected source. The signal originated from the center of the Milky Way. An accident changed astronomy. That discovery helped establish radio astronomy, allowing researchers to study wavelengths capable of penetrating regions that visible light could not cross. New instruments followed. Larger antennas appeared. Greater sensitivity emerged. Gradually, the hidden heart of the galaxy began revealing fragments of itself. Each generation extended the view. Infrared astronomy opened another window by detecting heat radiation passing through obscuring dust. X-ray observatories exposed energetic phenomena invisible at lower energies. Gamma-ray telescopes revealed extreme processes occurring across enormous scales. Submillimeter astronomy examined cold gas and dust with unprecedented detail. The picture expanded steadily. What you see today is the result of nearly 9 decades of technological development. From Jansky's simple rotating instrument to planet-sized telescope networks, every improvement depended upon countless engineers, programmers, technicians, mathematicians, and astronomers solving problems that earlier generations could barely define. The effort never belonged to one person. A powerful example came from Reinhard Genzel and Andrea Ghez. Working at different institutions on different continents, they spent more than 25 years tracking stars, racing around an unseen central object. Independent observations led both teams toward the same conclusion. A supermassive black hole occupied the galactic center. In 2020, the Nobel Prize recognized their achievement. Patience became evidence. The image of Sagittarius A star demanded an even larger collaboration. Telescopes located in Chile, Hawaii, Arizona, Spain, Mexico, and the South Pole observed simultaneously during narrow weather windows. Their recordings were combined using a technique called very long baseline interferometry, a method that links distant observatories into a single virtual telescope. The planet became the instrument. More than 300 researchers from 80 institutions across 21 countries contributed to that achievement. Years of preparation preceded a few days of observation. Then came years of analysis, calibration, verification, and reconstruction before the final image could emerge. Knowledge accumulated slowly. Science often appears to advance through dramatic moments: a photograph, a measurement, a confirmation. But those moments rest upon foundations built across decades. Every detector, every observatory, and every refinement in technique becomes part of a chain extending through generations. When we look toward the galactic center today, we are seeing more than a black hole. We are seeing the result of humanity's long determination to observe what once seemed unreachable, transforming faint signals from deep space into understanding through persistence, cooperation, and time. Consider the idea from the opposite direction for a moment. Instead of beginning with the black hole and asking what it does, we can begin with ourselves and ask what kind of galaxy made our existence possible. Every large spiral galaxy we have observed appears to possess a supermassive black hole at its center. The same pattern emerges again and again across the observable universe. Different sizes, different histories, different environments, yet the partnership remains. The connection runs deep. Evidence collected across decades suggests that galaxies and their central black holes do not develop independently. They grow together across cosmic time. Gas falling inward feeds the black hole. Energy flowing outward reshapes the galaxy. Each influences the future of the other. The relationship is architectural. Our galaxy is not merely a collection of stars surrounding an unrelated object, Sagittarius A. Star belongs to the structure itself. Its gravity helps organize the crowded central region. Its past activity altered the movement of gas. Its energetic episodes left marks that remain visible long after the original events ended. Those marks surround us. The vast gamma-ray structures, known as the Fermi Bubbles, the larger X-ray features, discovered by the extended Röntgen survey with an imaging telescope array mission, the glowing molecular clouds, and the immense magnetic filaments all preserve fragments of earlier chapters. Together, they form a record extending across millions of years, a history written in physics. When we examine these structures, we are reading traces of events no human witnessed. Radiation becomes evidence, magnetism becomes memory. Matter displaced long ago becomes a surviving archive. The galactic center stores information about transformations that occurred long before Earth formed its present landscapes. But another realization emerges. Our species exists during an unusually stable interval. The central black hole is presently faint. Star formation continues across the Milky Way. planetary systems orbit in relative calm. The conditions supporting life on Earth developed during a period that allowed complexity to flourish without major disruption from the galactic core. That chapter may be temporary. Past evidence shows alternating eras of activity and restraint. Energy surged outward, then conditions changed. New cycles followed. The galaxy evolved through both extremes. We happen to occupy one moment within that much longer story. The perspective can feel immense. Every atom of carbon inside your body was forged within ancient stars. Oxygen, calcium, iron, and countless other elements originated through stellar birth and stellar death, distributed across the Milky Way. Those processes unfolded inside a galaxy whose overall evolution was influenced, in part, by the object hidden at its center. We are connected to that history. The ground beneath us, the oceans, the atmosphere, and every living organism emerged from material shaped by events spanning billions of years. Some occurred near our region of the galaxy. Others were linked indirectly to processes unfolding much closer to Sagittarius A star. But perhaps the most remarkable detail is this. A collection of atoms produced by galactic evolution eventually became a species capable of studying that evolution. After billions of years of stellar cycles, one small world developed observers who can detect gamma rays, map magnetic fields, reconstruct ancient outbursts, and recognize that the story of the galactic center is also part of their own. If you could step far beyond the Milky Way and look back from intergalactic space, finding Earth would be impossible. Our world would disappear within a single star system. That star system would vanish among hundreds of billions of others, and the entire history of humanity would occupy a point too small to see. Yet its location matters. We live on the inner edge of the Orion Cygnus arm, a modest spiral structure winding through the galactic disk. From here, the distance to the galactic center is approximately 26,000 light years, or about 246 quintillion kilometers, which is about 153 quintillion miles. We occupy a position roughly halfway between the crowded core and the outer frontier of the galaxy. Neither extreme became our home. Closer to the center, stars gather in far greater numbers. Gravitational encounters occur more frequently. Radiation levels rise. Exploding stars become more common. The environment grows increasingly dynamic. Beautiful, certainly, but challenging for long periods of planetary stability. Farther outward, another problem appears. The outermost regions contain fewer generations of stars. Heavy elements become less abundant. Carbon, oxygen, silicon, iron, and other ingredients necessary for rocky planets and complex chemistry are produced inside stars and distributed through stellar death. Regions with fewer such generations possess fewer raw materials. Life may struggle there. This balance led astronomers and astrobiologists to propose the idea of a galactic habitable zone. The concept describes a range of distances from a galactic center where conditions appear especially favorable for long-term biological development. Too close, and the environment becomes disruptive. Too far, and essential elements become scarce. Between those extremes lies opportunity. Our solar system appears to reside comfortably within that range. The sun formed from material enriched by countless earlier stars. The rocky planets emerged from those elements. Oceans formed. Chemistry became increasingly complex. Eventually, living systems appeared and evolved over immense stretches of time. But our position provided more than ingredients. It also provided patience. For billions of years, Earth remained distant from the most energetic events occurring near the galactic center. Radiation diminished across vast expanses of space. Gravitational disturbances weakened with distance. The same galaxy that forged the materials of life also offered regions where those materials could organize themselves into something enduring. The arrangement feels almost architectural. The inner Milky Way produced generations of stars whose lives enriched the galaxy with heavier elements. Winds, explosions, and large scale galactic processes distributed that material outward through the disk. Some of it eventually became part of a molecular cloud that collapsed to form our Sun and its planets. We are descendants of that journey. The atoms composing mountains, oceans, forests, and human bodies originated within a much larger story. Their history stretches across spiral arms, stellar nurseries, and ancient generations of stars that vanished long before Earth existed. But distance completed the equation. The energetic heart of the galaxy helped supply the ingredients. Then 26,000 light years of separation, or about 246 quintillion kilometers, which is about 153 quintillion miles, provided room for those ingredients to persist, combine, evolve, and eventually become observers capable of understanding where they came from. A faint pattern hidden within radio static changed everything. In 1932, Carl Jansky was investigating interference affecting transatlantic telephone communications. Day after day, he rotated a large antenna and listened for repeating sources of noise. Most signals could be explained. Some came from nearby storms, others arrived from distant thunderstorms, yet one source returned with remarkable consistency. It followed the sky. The signal rose and fell according to a cycle linked not to Earth, but to the stars. Its source pointed toward the constellation Sagittarius, toward the crowded heart of our galaxy. Jansky did not know he had opened a new window onto the universe. He documented the discovery carefully. Then the signal entered scientific history. Everything we have explored traces back to that moment. The enormous structures extending above and below the galactic plane, the unexplained concentrations of high-energy radiation, the sudden brightening events near the central black hole, the magnetic fields wrapped around matter approaching the event horizon, the ancient outbursts recorded across distant gas clouds, even the distant spiral galaxy whose behavior offered a glimpse of possible futures, all emerged from humanity's effort to understand what that first signal meant. The story kept expanding. Across decades, new instruments arrived. Radio astronomy revealed hidden structures. Infrared observatories pierced obscuring dust. X-ray telescopes uncovered energetic processes. Gamma-ray detectors mapped colossal features stretching across the galaxy. Interferometers connected observatories across continents. Each advance added another sentence to a narrative already billions of years old. But our participation has been brief. The galactic center has been transmitting information across the electromagnetic spectrum for billions of years. We have been capable of listening for only about 90 years. Compared with the age of the Milky Way, that span is scarcely measurable. Yet what those years revealed is remarkable. The center of our galaxy is not an unchanging landmark. It is a dynamic system shaped by cycles of activity and dormancy. Energy accumulates. Matter falls inward. Magnetic fields organize. Outbursts reshape the surrounding environment. Then long intervals pass. Evidence remains. The record waits to be read. We happen to live during one of those calmer intervals. But calm does not mean inactive. It means we are observing a chapter between larger events. The traces surrounding the galactic center preserve episodes that occurred long before humanity appeared and long before Earth carried observers capable of understanding them. Consider where you are. You are resting on a planet orbiting an ordinary star, approximately 26,000 light years from the galactic center, or about 246 quintillion kilometers, which is about 153 quintillion miles. At that distance, the radiation, gravity, and history of the galaxy's core arrive only as diluted messages carried across immense expanses of space and time. Those messages continue. The Milky Way will evolve whether we observe it or not. Stars will form, stars will die. The central black hole will persist through cycles extending far beyond human timescales. But we are here now, able to detect those signals, decode their meaning, and place ourselves within a story that began long before our species existed. That is no small achievement. We are listening, and the galaxy is still speaking.